This is a supplementary lecture to polynomial regression in the executive black belt class. You can also think of this as sort of a general analytical technique that can be applied to the following circumstance. So we already know that for many cases we looked into if we have one x and one y, and strictly speaking if they're both number type variables, that we can make something called a scatter plot. And if that scatter plot happens to be something that we might want to fit to a line, we know that we can use either Excel or Minitab or Excel stats or whatever, and a little bit of statistical theory to create what is the best fit line, the line that best fits those. And we come up with a model that looks like a y. It doesn't help if you write black on black. Y equals B0 plus B1x, where these B1s, I'm sorry, these B0s and B1s actually come from calculations that we make in the data, and that we can then use that model for predictions. All right, that's all well and good, but what happens when you have a situation like this where your x and your y relationship is maybe, when you make that scatter plot, maybe it doesn't line up with a line, maybe it's something else. Like in this case, what happens if it's a curved relationship, right? Something like this. How do we find a fit that best makes sense there? All right. Now there's a number of different ways of doing it. However, one straightforward way of doing it, and it's almost like a brute force mathematical technique, is to look at what's called a polynomial. So a polynomial is nothing other than an expansion of a function based on its values raised to the first power, plus the values raised to the second power, etc., plus third power. So what we're going to do is we're going to look for a general expression that looks like this: y is equal to b0 plus b1x, b1 times x, and I'll just to be explicit here, I'll write x to the first power plus, I'll call this b2, x to the second power plus b2, b3, x to the third power plus dot, dot, dot. Generally, we want to stop around third. There will be cases where we want to go fourth. But let me be just perhaps more explicit even than this, is to say in a specific example, suppose y were, I don't know, fungus growth, right? Maybe growth of mushrooms, and x is the temperature that we expose these to. And maybe there's some physical growth curve that says, well, if you expand it, if you increase the temperature, you get some maximum, but then if you go beyond that, you get another minimum, and if you keep increasing, you get a maximum of a different type of fungus that grows. Who knows? You know, maybe the curve looks somewhat like that. So what we're talking about is we're looking at fungus growth. I'll call it Fg would be equal to B0 plus B1 times temp to the first power plus B2 temp to the second power plus B3 temp to the third power plus dot, dot, dot. Okay? That's the model that we're fitting. So notice, we still only have one variable. We're just raising it to multiple powers and putting it into our equation. Okay. Let's take a look at how to do that. Let's look at a couple of different examples. We'll look at one in Excel stats. We'll look at it in Minitab, and then we'll look at incorporating it with other techniques like multiple regression. Tends to be a 1x, 1y technique that we use. Generally speaking, 1x, 1y is when we're going to use this. However, there will be cases sometimes where you'll look at adding a polynomial into a more general expression. I just want to show you how to do that. That's all. Okay? So let's go to it. Let's look at a few examples. The first example I want to give is one that's actually in our binder. It's on alligators. And let's see if I can get that open. Here it is, right here. So let's write up our box. In this case, or think about it, in this case, if you let's suppose that you work for the Florida, you were a Florida Ranger, right? And if Parks and Recreation Department, one of the issues that you might have would be to kind of track the alligator population, and you may need to estimate the weight of alligators that are caught. Well, one thing might be I might not be that it might not be all that easy to measure a weight of an alligator, but I might be able to estimate the length of it pretty easily, right? To measure the weight, I might have to somehow sedate it, get it onto a scale, and then weigh it. Whereas if I wanted to get the length, maybe I could just estimate it, and it would be good enough. I wonder if I can predict the weight by using the length. Well, let's take a look at that. That's certainly, we have a num, and so maybe we can do that. So let's take a look. Well, when we do our 2num analysis, it's all well and good, but one of the things, at least when I look at the scatter plot, that I see is, hello, scatter plot, please. There we go. Back to the scatter plot. Is I don't see a line. Like if I just fit a line, maybe it would be kind of weird, but I kind of see a curve here instead of a line. So what if I wanted to fit that curve instead? Well, the sad part is I can't just go to correlation and linear regression, because look at the regression that it fits. Not that good, right? So I need to find something else. Polynomials to the rescue. So in Excel Stats, it's pretty straightforward. We simply go to Extra Tools. We go to Extra Tools, you'll see that at the upper left-hand corner there's function fitting. And there's lots of different ways we can do it. We can use linearizable functions. We can use polynomials, nonlinear regression. We are going to use polynomials, but let's just click on a button. We'll get them all. Okay. Actually, it turns out that nonlinear is pretty good. But anyway, let's go to, if you look on the bottom, here's a tab for polynomials. Go ahead and click on that. And when you do, you'll see that what Excel Stats does is it creates an estimate or a model for fitting a polynomial to this. And you can specify the degree of the polynomial that you want. So I'm just going to expand this out. Excel Stats always gives so many decimal points. Drives me crazy. There we go. Okay, so this is a little bit easier to read, I think. Let's even remove one more. There we go. Okay, so what I'm going to do is I'm going to change the degrees here. If you change the degree of the polynomial, that means just like if you do 0, that's just a constant. Let's see, that's not a very good model. If we do 1, that's our line. You see that? There's a length raised to the first power. If I do 2, it also puts in length to the second power. And I can keep doing that ad infinitum. I can put a third term in. I can put a fourth term in. I can go all the way up to 10, which I don't want to do. I want to stop at the one that's simplest and gives a pretty good explanation about what's going on. So if we look at the r squared, we can see how that changes as I add terms in. So my r equals to the first power, 83%. Not bad, but I can do better. If I click on the second power, 98.7%. If I click on the third power, 99.3. So I might stop at the third, or I might have even stopped at the second. And you can see here's the model that it comes up with. Okay? So it does the model for us, and which is pretty cool. All right. Let me show you how to. So basically, that's pretty much it. Let me show you how to do this in Minitab. First of all, I've got to get the right data in there, right? I've got to get the alligator data in. I'm going to pop it in right here next to the other stuff that we'll do in just a moment. And if you go to Stat, we can do it through regression, but it's kind of painful. We actually have to create another file, which is the length squared. I'm actually going to do that in Excel and copy it over. I'll call it L squared. I'll just call it length squared. How about that? And that's simply equal to the length times itself. Right? And we'll do the length cubed, which is equal to the length times itself twice. Oops. There we go. That's the length cubed. Okay, and then I'm just going to port that all to Minitab. It's the only time I'll do this, by the way. And we can use Minitab to go ahead and do this in the regular way that we were doing before. So that was to use multiple regression, stat regression, regression, and then we'll do weight by length, length squared, length cubed, and just let it rip. And we'll be able to see the p-values in there, right there. And there it gives us our r squared, and it gives us our equation. 278 plus 11.5 times length plus minus 0.15 times length squared, and so forth. 0.00807. We'll see that that's actually the same as what was in the Excel stats right there. See 0.000807 minus 0.15, 11.47, which is basically the same as 11.5, and 277.8. That also matches the Minitab of 278 right there. So it all is matching up, and we could do it just in that same way through multiple regression. It really is a multiple regression where we have multiple variables that are just expressions of the same variable. It's kind of weird. Luckily in Minitab, there's also a similar way of doing this all, which kind of is closer to Excel stats. Again, I like Excel stats because it comes up with the picture and puts that on there. You don't get the p-values. In order to do the p-values, you have to do what we just did in Excel stats, that is multiple regression by creating those additional columns. Not too fun, but to get the picture is kind of good. We can do that same picture in Minitab by going to Stat Regression, Fitted Line Plot, and choosing what we want. But we can only do one predictor at a time, which is kind of interesting. We can either do a linear, quadratic, or cubic model. We can't go above 3, x to the cubed power. So let's go ahead and do cubic, and you'll see Minitab comes up with that picture, puts in the equation right there, and gives us the r squared and all the rest of it. All right, so that's how to do it in there, and that's how, again, I might feel very comfortable measuring the length of an alligator and then using this model to say, let me plug in and see what the weight of that alligator is. Looks like this is a pretty darn good model. Okay, let's do a different example, and this should be very close to the example that's in your assignment. Let's go ahead and do that. The second example I want to do is on employee performance. And in this case, what we're looking at is we're looking at the time of the day, and we're looking at the employee performance. Now, the time of the day is not given in hours, but it's given in some normalized units where 50 is the end of the day. So it starts from your start of the workday, and so it has 50 demarcations during the day. Okay? And the performance is a measure of how productive the particular employees are. So let's go ahead and do that. Look in Excel stats, that's 2num. And whoops, I've got my X's and Y's mixed up. There we go. So if we did that, we can certainly see again that we probably wouldn't want to fit a line to that, which is fit right here. We can see certainly that that's not going to look good. Again, if we look at residuals, we'll see that pattern where it's that rainbow sort of pattern. See that? Okay, so what can we do? Well, we can fit a polynomial. Transformation is not going to help us here, but a polynomial might. So let's try our polynomial. And there we go. There's degree 1. There's degree 0. Just pick the average. There's degree 1. I don't like it. It certainly doesn't get the end of the rainbow there. And degree 2. That's probably good. I mean, if I look at the r squared, I'm going from 29% to 87% by going from 1 to 2. When I go to 3, it doesn't really improve much. So I'm going to stop at 2 using our Occam's razor approach. Okay, and there we have it. There's our model right there. So again, this looks like a pretty darn good model if you were going to use this to predict the performance of an employee based on the time of day. If you had this data, it looks like that's not a bad model. It certainly is a lot better, 87% r squared, and fits the data pretty well without being overly fitting. We're only using 2-degree polynomial, which isn't too bad. And again, it definitely sort of describes this whole idea of, yeah, you start, and maybe you're not into high gear. By 10 o'clock, you're starting to get into high gear. Maybe by the 3 o'clock time period, you're starting to end it. And by the end of the day, your performance is starting to drop, but it's time to go home. Model captures it pretty well. So there you have it. That's it. Okay, it would work very similarly in Minitab. Just to show you, let's do it. Stat, regression, fitted line plot. Performance is my output. Time of day is my input. I'm only going to fit the quadratic this time. Click okie dokie, and bam, there we go. Again, it fits it pretty well. All right, I have one more to do here. And the last one I wanted to do was an example from what happens if we want to add in what happens if we have a regression and we want to add in other variables. So let's take a look at that. So what would happen if, we already know how to do a multiple regression if we're looking for, here's an example, a very simplified example of the cars. In this case, we're looking to predict highway miles per gallon by fuel capacity and weight, which were two of the variables that we found were significant in the model that we did for multiple regression. But in this case, suppose that we, for some reason, decided to look at these separately, and we looked at highway miles per gallon versus fuel capacity first. Let's take a look at that. When we do a two-num analysis, maybe you might say, well, that's a little bit of a curvy relationship, and the line isn't looking so good. So I'm going to use a polynomial to do that. So let me go ahead and do this. And if we look at a polynomial fit, maybe you said, well, just by putting in that slight curvature, I improved the model from 61 to 63, but I got enough of an improvement to really keep it. So I'm going to go ahead and keep that in there. And now I want to add that second order term into my model for multiple regression. How would I do that? Well, I won't say it's simple, but it's pretty straightforward. You simply, just to make this easier, you would simply add another fuel capacity squared, I'll call it FC squared, into your model. You create another column that actually has the variable, like so. Okay, and now, just to prove that we actually do get the same thing, if I chose this and did a multiple regression, n-num this time, I should get the same coefficients that I got for my polynomial. And in fact, when I come over here, I'm just going to note this, 64 minus 2.9, 0.05. That's what I got in my model. If I look at my This is it. If I look at my polynomial, there it is, 65 minus 2.9.05. So I got the same model, 63%, 63.8% r squared. See if I got that. There it is right there, 63.8% r squared. There it is right there. So it's the same model. Okay? So I just wanted to prove that to you. And what if I wanted to add then not just fuel capacity and fuel capacity squared, but what if I wanted to add weight to that? It's just simply, let's go ahead and make the multiple regression model now choosing all of these. So you can combine if you want. And here it is. Now we have fuel capacity squared, we have weight, we have all of those in our model, which is now given right there. You see that? They're all in there. All right? So that's how you would do it in Excel Stats. In Minitab, very similar. I'm just going to port this whole thing over. But actually, Minitab can do slightly better than Excel Stats in this way because it has a little bit of an automatic facility to do this. We don't actually need FC squared, as I'll show you in a moment. We can put it directly in the model. If we wanted to use FC squared, we could go ahead and do stat regression, just like we did before, and add them all in, hit the OK button, and we would get regular Minitab just like we always did. Okay? That's exactly the same results that we got from running the Excel Stats. And that's exactly what we've done before. However, Minitab does have a facility called general regression. And if you want to look into it, it may be helpful to you. You can actually type in models that you want using the initial data. So I might have highway miles per gallon is equal to fuel capacity, and I might want to put in fuel capacity squared. That's how you do it in the model. That's just Minitab notation. See, I don't have to put in FC squared. I could just square fuel capacity right in there. And I want to add weight in there as well. And if I click that, I should be able to get the same result that I had before. Just as a benchmark, let's look and make sure that we get the 68% r squared adjusted of 67.2, 68.3 and 67.2. Let's see if we get the same thing. We do. So it really is the same output. And if you do look back and you want to repeat this, you'll find that you get the same p-values, the same model, and everything. It's just a different thing in Minitab where you can do things and combine a little bit easier. Okay, that's it. So I hope that especially the first two examples you found illuminating. In Excel Stats, you simply click on the polynomial regression. In Minitab, you have this fitted line plot, which can be helpful. So just a quick recap. When we're doing polynomial regression, very straightforward. When we look at, generally speaking, 1x and 1y, and this is generally when it's used, if we have a curve that looks like we can fit to a line, that's great. Let's go ahead and use a line. However, if we have something that is not a curve, that is not a line, but can be fit to a curve, we'll use that. We'll use polynomial regression, and that can help us better fit that. Okay? And here's what the equation looks like. Instead of just y equals b plus b1x, we may have higher order terms. X to the first, x squared, and x cubed. All right, thanks a lot, and hope you got something out of this lecture and that you enjoyed it, and we'll see you next time.